Igneous rock is one of the three main rock types, the others being sedimentary and metamorphic. Igneous rock is formed through the cooling and solidification of magma or lava. Igneous rock may form with or without crystallization either below the surface as intrusive rocks or on the surface as extrusive rocks. This magma can be derived from partial melts of pre-existing rocks in either a planet's mantle or crust. Typically, the melting is caused by one or more of three processes: an increase in temperature, a decrease in pressure, or a change in composition. Over 700 types of igneous rocks have been described, most of them having formed beneath the surface of Earth's crust. Geological significance: igneous and metamorphic rocks make up 95% of the top 16 km of the Earth's crust by volume. Igneous rocks are geologically important because their minerals and global chemistry give information about the composition of the mantle, from which some igneous rocks are extracted, and the temperature and pressure conditions that allowed this extraction, and/or of other pre-existing rock that melted. Their absolute ages can be obtained from various forms of radiometric dating and thus can be compared to adjacent geological strata, allowing a time sequence of events. Their features are usually characteristic of a specific tectonic environment, allowing tectonic reconstitutions. In some special circumstances they host important mineral deposits. For example, tungsten, tin, and uranium are commonly associated with granites and diorites, whereas ores of chromium and platinum are commonly associated with gabras. Morphology and setting. In terms of modes of occurrence, igneous rocks can be either intrusive, extrusive or hypabyssal. Intrusive. Intrusive igneous rocks are formed from magma that cools and solidifies within the crust of a planet, surrounded by pre-existing rock. The magma cools slowly and, as a result, these rocks are coarse-grained. The mineral grains in such rocks can generally be identified with the naked eye. Intrusive rocks can also be classified according to the shape and size of the intrusive body and its relation to the other formations into which it intrudes. Typical intrusive formations are batholiths, stocks, laccoliths, sills and dikes. When the magma solidifies within the Earth's crust, it cools slowly, forming coarse textured rocks, such as granite, gabbro, or diorite. The central cores of major mountain ranges consist of intrusive igneous rocks, usually granite. When exposed by erosion, these cores may occupy huge areas of the Earth's surface. Coarse-grained intrusive igneous rocks that form at depth within the crust are termed as abyssal. Intrusive igneous rocks that form near the surface are termed hypabyssal. Extrusive. Extrusive igneous rocks, also known as volcanic rocks, are formed at the crust's surface as a result of the partial melting of rocks within the mantle and crust. Extrusive igneous rocks cool and solidify quicker than intrusive igneous rocks. They are formed by the cooling of molten magma on the Earth's surface. The magma, which is brought to the surface through fissures or volcanic eruptions, solidifies at a faster rate. Hence such rocks are smooth, crystalline and fine-grained. Basalt is a common extrusive igneous rock and forms lava flows, lava sheets and lava plateaus. Some kinds of basalt solidify to form long polygonal columns. For example, the Giant's Causeway in Antrim, Northern Ireland. The melted rock, with or without suspended crystals and gas bubbles, is called magma. It rises because it is less dense than the rock from which it was created. When magma reaches the surface from beneath water or air, it is called lava. Eruptions of volcanoes into air are termed subaerial, whereas those occurring underneath the ocean are termed submarine. Black smokers and mid-ocean ridge basalt are examples of submarine volcanic activity. The volume of extrusive rock erupted annually by volcanoes varies with plate tectonic setting. Extrusive rock is produced in the following proportions: divergent boundary, 73%, convergent boundary, 15%, hotspot, 12%. Magma that erupts from a volcano behaves according to its viscosity, determined by temperature, composition, and crystal content. High-temperature magma, most of which is basaltic in composition, behaves in a manner similar to thick oil and, as it cools, treacle. Long, thin basalt flows with pahio surfaces are common. Intermediate composition magma, such as andesite, tends to form cinder cones of intermingled ash, tuff and lava, and may have a viscosity similar to thick, cold molasses or even rubber when erupted. Felsic magma, such as rhyolite, is usually erupted at low temperature and is up to 10,000 times as viscous as basalt. Volcanoes with rhyolitic magma commonly erupt explosively, and rhyolitic lava flows are typically of limited extent and have steep margins, because the magma is so viscous. Felsic and intermediate magmas that erupt often do so violently, with explosions driven by the release of dissolved gases typically water vapor, but also carbon dioxide. Explosively erupted pyroclastic material is called tufa and includes tuff, agglomerate and ignimbrite. Fine volcanic ash is also erupted and forms ash-tuff deposits, which can often cover vast areas. Because lava cools and crystallizes rapidly, it is fine-grained. If the cooling has been so rapid as to prevent the formation of even small crystals after extrusion, the resulting rock may be mostly glass. If the cooling of the lava happened more slowly, the rocks would be coarse-grained. Because the minerals are mostly fine-grained, it is much more difficult to distinguish between the different types of extrusive igneous rocks than between different types of intrusive igneous rocks. Generally, the mineral constituents of fine-grained extrusive igneous rocks can only be determined by examination of thin sections of the rock under a microscope, so only an approximate classification can usually be made in the field. Hypabyssal igneous rocks are formed at a depth in between the plutonic and volcanic rocks. These are formed due to cooling and resultant solidification of rising magma just beneath the Earth's surface. Hypabyssal rocks are less common than plutonic or volcanic rocks and often form dikes, sills, laccoliths, lopoliths, or phacholiths. Classification: igneous rocks are classified according to mode of occurrence, texture, mineralogy, chemical composition, and the geometry of the igneous body. The classification of the many types of different igneous rocks can provide us with important information about the conditions under which they formed. Two important variables used for the classification of igneous rocks are particle size, which largely depends on the cooling history, and the mineral composition of the rock. Feldspars, quartz or feldspathoids, olivines, pyroxenes, amphiboles, and micas are all important minerals in the formation of almost all igneous rocks, and they are basic to the classification of these rocks. All other minerals present are regarded as non-essential in almost all igneous rocks and are called accessory minerals. Types of igneous rocks with other essential minerals are very rare, and these rare rocks include those with essential carbonates. In a simplified classification, igneous rock types are separated on the basis of the type of feldspar present, the presence or absence of quartz, and in rocks with no feldspar or quartz, the type of iron or magnesium minerals present. Rocks containing quartz are silica oversaturated. Rocks with feldspathoids are silica undersaturated, because feldspathoids cannot coexist in a stable association with quartz. Igneous rocks that have crystals large enough to be seen by the naked eye are called phaneritic. Those with crystals too small to be seen are called aphanitic. Generally speaking, phaneritic implies an intrusive origin. Aphanitic an extrusive one. An igneous rock with larger, clearly discernible crystals embedded in a finer-grained matrix is termed porphyry. Porphyritic texture develops when some of the crystals grow to considerable size before the main mass of the magma crystallizes as finer-grained, uniform material. Igneous rocks are classified on the basis of texture and composition. Texture refers to the size, shape, and arrangement of the mineral grains or crystals of which the rock is composed. Texture. Texture is an important criterion for the naming of volcanic rocks. The texture of volcanic rocks, including the size, shape, orientation, and distribution of mineral grains and the intergrain relationships, will determine whether the rock is termed a tuff, a pyroclastic lava or a simple lava. However, the texture is only a subordinate part of classifying volcanic rocks, as most often there needs to be chemical information gleaned from rocks with extremely fine-grained ground mass or from F-fall tuffs, which may be formed from volcanic ash. Textural criteria are less critical in classifying intrusive rocks where the majority of minerals will be visible to the naked eye or at least using a hand lens, magnifying glass or microscope. Plutonic rocks also tend to be less texturally varied and less prone to gaining structural fabrics. Textural terms can be used to differentiate different intrusive phases of large plutons, for instance porphyritic margins to large intrusive bodies, porphyry stocks and subvolcanic dikes. Mineralogical classification is most often used to classify plutonic rocks. Chemical classifications are preferred to classify volcanic rocks, with phenocryst species used as a prefix, for example olivine-bearing peakrite, or orthoclaspheric rhyolite. See also List of rock textures and igneous textures. Chemical classification. Igneous rocks can be classified according to chemical or mineralogical parameters. Chemical, total alkali silica content for volcanic rock classification used when modal or mineralogic data is unavailable. Felsic igneous rocks containing a high silica content, greater than 63% CO2, intermediate igneous rocks containing between 52–63% CO2, mafic igneous rocks have low silica 45–52% and typically high iron magnesium content. Ultramafic rock igneous rocks with less than 45% silica, alkalic igneous rocks with 5–15% alkali content or with a molar ratio of alkali to silica greater than 1:6. Chemical classification also extends to differentiating rocks that are chemically similar according to the TAS diagram, for instance, ultrapotassic rocks containing molar K2O Na2O greater than 3, per-alkaline. Rocks containing molar/Al2O3 greater than 1, per-aluminous. Rocks containing molar/Al2O3 less than 1, an idealized mineralogy can be calculated from the chemical composition, and the calculation is useful for rocks too fine-grained or too altered for identification of minerals that crystallized from the melt. For instance, normative quartz classifies a rock as silica oversaturated. An example is rhyolite. In an older terminology, silica oversaturated rocks were called silicic or acidic where the CO2 was greater than 66% and the family term quartzolite was applied to the most silicic. A normative feldspathoid classifies a rock as silica undersaturated. An example is nephelinite. History of classification. In 1902, a group of American petrographers proposed that all existing classifications of igneous rocks should be discarded and replaced by a quantitative classification based on chemical analysis. They showed how vague, and often unscientific, much of the existing terminology was and argued that as the chemical composition of an igneous rock was its most fundamental characteristic, it should be elevated to prime position. Geological occurrence, structure, mineralogical constitution the hitherto accepted criteria for the discrimination of rock species were relegated to the background. The completed rock analysis is first to be interpreted in terms of the rock-forming minerals which might be expected to be formed when the magma crystallizes, for example, quartz feldspars, olivine, aconite, feldspathoids, magnetite, corundum, and so on, and the rocks are divided into groups strictly according to the relative proportion of these minerals to one another. Mineralogical classification. For volcanic rocks, mineralogy is important in classifying and naming lavas. The most important criterion is the phenocryst species, followed by the ground mass mineralogy. Often, where the ground mass is aphanitic, chemical classification must be used to properly identify a volcanic rock. Mineralogic intents Felsic versus mafic. Felsic rock, highest content of silicon, with predominance of quartz, alkali feldspar and/or feldspathoids, the felsic minerals. These rocks are usually light-colored, and have low density. Mafic rock, lesser content of silicon relative to felsic rocks, with predominance of mafic minerals pyroxenes, olivines and calcic plagioclase. These rocks are usually dark-colored, and have a higher density than felsic rocks. Ultramafic rock, lowest content of silicon, with more than 90% of mafic minerals. For intrusive, plutonic and usually phenoritic igneous rocks, the mineralogy is used to classify the rock. This usually occurs on ternary diagrams, where the relative proportions of three minerals are used to classify the rock. The following table is a simple subdivision of igneous rocks according to both their composition and mode of occurrence. For a more detailed classification, see QAPF diagram. Example of classification: granite is an igneous intrusive rock, with felsic composition and phenolitic, subahedral texture. Magma origination: the Earth's crust averages about 35 km thick under the continents, but averages only some 7–10 km beneath the oceans. The continental crust is composed primarily of sedimentary rocks resting on a crystalline basement formed of a great variety of metamorphic and igneous rocks, including granite and granite. Oceanic crust is composed primarily of basalt and gabbro. Both continental and oceanic crust rest on peridotite of the mantle. Rocks may melt in response to a decrease in pressure, to a change in composition, to an increase in temperature, or to a combination of these processes. Other mechanisms, such as melting from a meteorite impact, are less important today, but impacts during the accretion of the Earth led to extensive melting, and the outer several hundred kilometers of our early Earth was probably an ocean of magma. Impacts of large meteorites in the last few 100 million years have been proposed as one mechanism responsible for the extensive basalt magmatism of several large igneous provinces. Decompression melting occurs because of a decrease in pressure. The solidus temperatures of most rocks increase with increasing pressure in the absence of water. Peridotite at depth in the Earth's mantle may be hotter than its solidus temperature at some shallower level. If such rock rises during the convection of solid mantle, it will cool slightly as it expands in an adiabatic process, but the cooling is only about 0.3 degrees Celsius per kilometer. Experimental studies of appropriate peridotite samples document that the solidus temperatures increase by 3 degrees Celsius to 4 degrees Celsius per kilometer. If the rock rises far enough, it will begin to melt. Melt droplets can coalesce into larger volumes and be intruded upwards. This process of melting from the upward movement of solid mantle is critical in the evolution of the Earth. Decompression melting creates the ocean crust at mid-ocean ridges. It also causes volcanism in intraplate regions, such as Europe, Africa and the Pacific sea floor. There, it is variously attributed either to the rise of mantle plumes or to intraplate extension. Effects of water and carbon dioxide: the change of rock composition most responsible for the creation of magma is the addition of water. Water lowers the solidus temperature of rocks at a given pressure. For example, at a depth of about 100 kilometers, peridotite begins to melt near 800 degrees Celsius in the presence of excess water, but near or above about 1500 degrees Celsius in the absence of water. Water is driven out of the oceanic lithosphere in subduction zones, and it causes melting in the overlying mantle. Hydrous magmas composed of basalt and andesite are produced directly and indirectly as results of dehydration during the subduction process. Such magmas, and those derived from them, build up island arcs such as those in the Pacific Ring of Fire. These magmas form rocks of the calc-alkaline series, an important part of the continental crust. The addition of carbon dioxide is relatively a much less important cause of magma formation than the addition of water, but genesis of some silica undersaturated magmas has been attributed to the dominance of carbon dioxide over water in their mantle source regions. In the presence of carbon dioxide, experiments document that the peridotite solidus temperature decreases by about 200 degrees Celsius in a narrow pressure interval at pressures corresponding to a depth of about 70 km. At greater depths, carbon dioxide can have more effect. At depths to about 200 km, the temperatures of initial melting of a carbonated peridotite composition were determined to be 450 degrees Celsius to 600 degrees Celsius lower than for the same composition with no carbon dioxide. Magmas of rock types such as nephelinite, carbonatite, and kimberlite are among those that may be generated following an influx of carbon dioxide into mantle at depths greater than about 70 km. Temperature increase in temperature is the most typical mechanism for formation of magma within continental crust. Such temperature increases can occur because of the upward intrusion of magma from the mantle. Temperatures can also exceed the solidus of a crustal rock in continental crust thickened by compression at a plate boundary. The plate boundary between the Indian and Asian continental masses provides a well-studied example, as the Tibetan Plateau just north of the boundary has crust about 80 kilometers thick, roughly twice the thickness of normal continental crust. Studies of electrical resistivity deduced from magnetotelluric data have detected a layer that appears to contain silicate melting that stretches for at least 1,000 kilometers within the middle crust along the southern margin of the Tibetan Plateau. Granite and rhyolite are types of igneous rock commonly interpreted as products of the melting of continental crust because of increases in temperature. Temperature increases also may contribute to the melting of lithosphere drag down in a subduction zone. Magma evolution. Most magmas only entirely melt for small parts of their histories. More typically, they are mixes of meltant crystals, and sometimes also of gas bubbles. Melt, crystals, and bubbles usually have different densities, and so they can separate as magmas evolve. As magma cools, minerals typically crystallize from the melt at different temperatures. As minerals crystallize, the composition of the residual melt typically changes. If crystals separate from the melt, then the residual melt will differ in composition from the parent magma. For instance, a magma of gabbroic composition can produce a residual melt of granitic composition if early formed crystals are separated from the magma. Gabbro may have a liquidus temperature near 1200 degrees Celsius, and the derivative granite composition melt may have a liquidus temperature as low as about 700 degrees Celsius. Incompatible elements are concentrated in the last residues of magma during fractional crystallization and in the first melts produced during partial melting. Either process can form the magma that crystallizes to pegmatite, a rock type commonly enriched in incompatible elements. Born's reaction series is important for understanding the idealized sequence of fractional crystallization of a magma. Magma composition can be determined by processes other than partial melting and fractional crystallization. For instance, magmas commonly interact with rocks they intrude, both by melting those rocks and by reacting with them. Magmas of different compositions can mix with one another. In rare cases, melts can separate into two immiscible melts of contrasting compositions. There are relatively few minerals that are important in the formation of common igneous rocks, because the magma from which the minerals crystallize is rich in only certain elements: silicon, oxygen, aluminium, sodium, potassium, calcium, iron, and magnesium. These are the elements that combine to form the silicate minerals, which account for over 90% of all igneous rocks. The chemistry of igneous rocks is expressed differently for major and minor elements and for trace elements. Contents of major and minor elements are conventionally expressed as weight % oxides. Abundances of trace elements are conventionally expressed as parts per million by weight. The term trace element is typically used for elements present in most rocks at abundances less than 100 ppm or so, but some trace elements may be present in some rocks at abundances exceeding 1000 ppm. The diversity of rock compositions has been defined by a huge mass of analytical data. Over 230,000 rock analyses can be accessed on the web through a site sponsored by the U.S. National Science Foundation. Etymology: the word igneous is derived from the Latin ignis, meaning of fire. Volcanic rocks are named after Vulcan, the Roman name for the god of fire. Intrusive rocks are also called plutonic rocks, named after Pluto, the Roman god of the underworld. See also, List of minerals, List of rock types, Large igneous province, Petrology, Metamorphic rocks, Sedimentary rocks, Notes. References: R.W. Lemaitre. Igneous rocks, a classification and glossary of terms, recommendations of the International Union of Geological Sciences, Subcommission of the Systematics of Igneous Rocks, Cambridge, Cambridge University Press. ISBN 0-520-66215-X, external links, USGS Igneous Rocks, Igneous Rock Classification Flow Chart, Igneous Rocks Tour, An Introduction to Igneous Rocks, the IUGS Systematics of Igneous Rocks.